For the introduction, my name is Gaetano Marrocco, University of Roma Vergata. And in this talk, I will discuss about how can we fabricate physical unclonable functions by using flexible antennas made by laser-induced graphene. And I will show you how we can transform imperfections into information. Okay, what is a physical unclonable function? A physical unclonable function is a device that when is challenged by a physical stimuli will provide an output signal. And this output signal is related to the challenge by means of internal random behavior. It can work like a physical fingerprint of the device and should be easy to read. Moreover, it should be also unclonable. What does it mean, unclonable? Sorry, but I took probably a wrong presentation. Why unclonable? Unclonable means that if you have two identical devices and you make a unique, simple, similar challenge, you will obtain different response. And even if you know the couplets of challenge and the response for any device, you are not able to reproduce because this relationship is related to the internal imperfection. And so we can use this device as a physical layer authentication that can be a complete digital one. Well, how can we fabricate this physical unclonable function? We can use the laser-induced graphene. The laser-induced graphene is a process to fabricate graphene by using a laser that engraves a surface. And when engraved the surface, it will provide some fluffy behavior of graphene, and the surface should be rich of carbon. And the very important topic is that we have many different settings so that we can obtain different values of surface conductivity, different morphologies from one case to another, but also if we move from one place to another, we could have a different morphology. So this is the random behavior that we can use to extract information. In fact, let's consider these three antennas. These three antennas, they are identical in shape. They have been fabricated by the same laser settings, but if we give a look to this boundary here, they look different. And if we perform an interrogation at the microwaves close to 1 gigahertz by using the standard RFID protocol, we will have a response that will include the information about this internal difference. So what we need to do is to extract this information. Okay, just a few maths. You can consider the transmitter. The transmitter will generate different input power at different frequency, and we have the response. The response is essentially a processing of the voltage that is scattered back by the device. And then if we repeat this interrogation for different value of power and frequencies, we will have a vector of different response and challenges. Then we need to make just a few processing. This is the rough response, and that includes both the large-scale variation that is due to the geometry of the device, so it's the same for any device you consider of the same shape. Then we have a small variation, small-scale variation, which is said related to the imperfection. So we need to extract this small variation so we can perform a detrending, just have this small oscillation, then we can perform an equalization, and finally we can apply a digital encoding by a number of bits which is related to the noise. So we have to compute case by case, and so finally we have the digital string. This is related to just a single challenge. So what we have is a database of, if we have many devices, where each block is a block of 1 and zeros. The rows are related to the power challenges, and the column are related to the frequency. We can use all this information or a subset. Okay, then we need to evaluate how good in cryptography meaning is our key. So we can analyze the randomness by using the Shannon entropy, let's say the probability to have a 0 or a 1 in any pixel or my database, and it should be close to 1. It means that in any position we have 50% of percentage of probability to a 1 or 0. It's completely, say, very difficult for an attacker to make crypto analysis to try to derive the key. Then we have the Hamming distance. We consider couplets of challenge or devices, and we evaluate how many bits are different. And to have the better correlation, it should be close to 0.5. So we cannot have any possibility to correlate one response to the other. Once we make this analysis, we can evaluate the degrees of freedom, let's say the number of bits which are independent. Now, once we have the number of bits, we can evaluate the encoding capabilities. Let's say how many independent keys can we generate by this specific process. I will show you better with an example. And we have one possibility of just considering intrinsic variability. Let's say just the variability on the same shape due to the laser imperfection. And then we have an engineered variability. We will introduce some additional defects to increase the degrees of freedom. To have reliable measurement, we fabricated a holder, plastic holder, where we introduced the antenna. Then we have a small loop here to couple the energy with the graphene. And in the loop, we have a microchip to establish a standard RFID communication. What is typical is that this small loop is over inside the plastic board. So we will have information just related to the imperfection, not to the specific response of the IC. The sounding, the challenging is made by a conventional RFID measuring system. And I would like to show you that we are at a distance of 30 centimeters. So we don't need to stay just in touch with the device. We can also get information from a given distance. Okay, let's consider the intrinsic variability. We have 30 antennas, and in every diagram we have the response of all the 30 antennas for different value of impinging power. After the training and equalization, you can see that the differences are really visible. Now we can perform digital encoding, and finally we have the PUF database on my system, where 1 is encoded by a white pixel, 0 by a black pixel, while yellow means that for the combination of power and frequency, we don't have any response from the antenna because the power collected is too low. And so every device will provide the magenta region that you can use, as I told you, as a wall or just piece by piece. Analysis, cryptographic analysis. These are the Shannon entropy with respect to row and with respect to column. That is why here there is an error. And in all the cases, the distribution tends to 1. 1 means, as I told you, that every bit position has about 50% of 0 and 50% of 1. So if we perform statistics, you cannot get any information about the cryptographic distribution. Then, how unique is this database of key? We can analyze the inter-Hamming distance. So every pixel is the Hamming distance between 2 devices with the same power challenge. And you can see they are close to 0.5, means they are uncorrelated. The black one means each device against itself. So, of course, you will have 0 value, no difference. In the other diagram, instead, we have the intra-Hamming distance. Intra-Hamming means that for each pixel is related to the same device, but with 2 different power challenges. And also in this case, the behavior is the same. So it means it's very incredible, because if you change the input power, you could have two different keys, independent keys from the same device. And if we evaluate the degrees of freedom, we have 160 bits corresponding to this value of power, so that we could, in theory, generate more than 10 at 35 power different keywords. Then the experiment with engineering variability, we introduce here some defects. These defects are a region where we have used different laser parameters to introduce not only defects on the boundaries ears, but also a different sheet resistance. So the current will be disturbed by these defects, and we will have not only small scale variation, but also large scale variation. And in fact, if we see the raw signal before processing with just 4 devices, you can observe not only a local variability, but also a macro scale variability, which is related to the defect we are introducing. So we can use both this information, and to this purpose, we can introduce the discrete Weber transform to get both the approximation, let's say the large scale variation, and the detail, let's say small scale variation. If we put all together, we will have an example that is not statistically significant, because 4 elements are not enough, but we have some information, and we can say here that also in this case we have a mean ambient distance close to 0.5, a Shannon theory entropy close to 1, but the estimated degrees of freedom is more than 200. And so the capacity of encoding is even larger. So in conclusion, by using the imperfection of the laser-induced graphene process technique, we could generate secure key that we can use for authentication. And it is important that we are using the same protocol for identification sensing, which is standard for RFID technology. So you will have identification, sensing, and physical layer, identification, sensing, and physical layer, say anti-counterfeiting, that you can say put in parallel with the digital security. We had more than 200 independent bits. And just to give a value to this name, consider that your smart card, Visa, MasterCard, or other, has between 128 and 256 bits. So the degrees of security of this physical layer is comparable to what we have with digital protocols, security protocols of the smart card. But we can do probably in the future even better when we learn how to master even better the engineering on macro defect. Now there are still activity ongoing, and in particular, one of these is to analyze the stability over time. And we already made experiments in near field, let's say, getting the information just very close to the antenna. We have much more data that increase the degrees of freedom. That's all. Thank you for the attention.